Hey everybody, this video is talking about something known as the inverse square law. It's actually an effect seen in physics. It's not necessarily its own specific physics topic, it's a pattern. In fact, we've seen this pattern already a couple of times in our class, even though we've never described this. So we're going to see what this is actually saying and how it has shown up or where it's shown up in some of the physics that we've already learned, okay? To understand this inverse square law, there is a classic thought experiment. There's this classic example called the butter gun. If you're in my own class, we already may have watched a video describing it, but here it is in a nutshell. Let's say I want to put butter on a piece of bread, and I have invented the butter gun, meaning I have this gun that I can load up with butter. It will then shoot butter to coat my piece of bread, okay? So I've done that. I've taken a single slice of bread, I put it a certain distance away from my butter gun, I fired the butter gun, and this is what I get. And, this isn't terrible, except, man, that's some really thick butter on there. I don't really want the butter to be that thick. So I actually move the butter gun back, all right? And when I move the butter gun back and I fire it, now I have a nicer, not as thick spread of butter, but you can kind of tell over here, the butter spreads out. It's not just on one piece of bread. If there weren't these other 3 pieces, 4 in total, I'd have just butter all around here. So by moving the butter gun back, I'm able to get a thinner coating of butter, but also that butter spreads out, okay? Farther away, we can cover more bread. That's the basic idea of this butter gun. If I move the gun farther back, I am able to coat more pieces of bread. Now, I've actually kind of hinted at it, but what's the downside of this? This first statement up here seems pretty great. Oh, I want to cover more bread. All I have to do is move the butter gun farther and farther back. But, what's the downside of that? Or, to be honest, if you're what are you even talking about with this butter gun thing? Think of a can of spray paint. Spray paint does the same idea. If I move the spray paint can farther back before I spray it, I will cover more area, more wall. But again, I ask, what is the downside? Is it just as simple as all you got to do is move farther back and then you coat more things? Maybe you recognize, well, if you're farther and farther back, you will cover more area, more bread or more wall, but the paint or the butter is getting spread out, it is getting weaker, it is getting thinner. You don't have as strong a coating of spray paint. The intensity of whether it's butter or spray paint, the intensity goes down. Everybody, instead of the word intensity, you could say the word strength. All right, to be honest, this is kind of a broad idea and it shows up in a variety of different ways. There's no single best word here. So intensity or strength, even though those aren't exactly physics words, is a good term to be using here. When you move the butter gun or when you move a can of spray paint further back, it will cover more area, but also the strength or the thickness or the intensity, it goes down. And here's a static image showing this idea. We're not seeing the gun moving back, we're just seeing different distances. At a certain distance, the butter is going to cover one piece of bread. But if the distance was twice as much, the butter spreads out. We can kind of see with this cone shape, the butter is spreading out as it travels. But again, there's a caveat. Since here it only had to cover one piece of bread, it got all the thickness. Over here, now the butter is spreading out. It's now covering 4 pieces of bread, so the thickness is 1/4 on each. It's getting less intense. Over here, if I'm now 3 times the distance, well, 3 times the distance, I can actually cover 9 pieces of bread. But what's the downside? As before, 1 piece used to get all the butter. Now 9 pieces are getting it, so it's 1/9 as intense. The butter thickness is 1/10. Again, imagine replacing this with a can of spray paint. The farther away the wall is, the wider area, but the thickness of that spray paint is going to be less, all right? Force, strength, intensity, whatever you want to call it, it has to spread out to cover a larger area. And because it's spreading out to cover a larger area, that intensity lessens. It decreases. It gets smaller and smaller and smaller. This is a GIF. This is an animation showing sunlight. Sunlight, as it travels through outer space, spreads out. I like this animation. I'm not exactly sure how many waves of light they're showing. Maybe there's 9 or maybe there's 10. I actually haven't counted. But all of them go through this first area of A, but twice as far back. Do you notice? Some of the light now is going through other pockets, so not as much light is going through the same area as before. This one gets all the waves of light, and then here only 3 of those light waves. So that light is spreading out. The intensity of the light is getting smaller. Same image, just stagnant, but it's showing, again, As that light is traveling, as it's going farther and farther out, the light is spreading out, which is nice, but the downside, the intensity, how much, say, light there is in a given square, gets less and less. It gets weaker and weaker and weaker. I may have asked this question if you're in my own class, but what fraction of light from the sun do you think makes it all the way to the Earth? The sun is pumping out light in all directions. The sun is a sphere. What fraction, what percent of light emitted from the sun makes it to the Earth? Well, it spreads out as it travels, but that also means the intensity gets weaker. Team, this number right here, that's the percentage of light that actually hits the Earth. It is a teeny tiny fraction, a minuscule percent of all the light from the sun is actually hitting the Earth. So when it's nice and hot out on a sunny day and you're feeling that brightness, that intensity from the sun, recognize that we are only getting the smallest of fractions of light from the sun. It would be much higher percent if Earth was closer, all right? Okay, team, this is a graph representing this idea, and this is a very important graph, but I get it, it's weird at first. On this y-axis, it's showing intensity, and on this x-axis, it's showing distance. They're using r for distance. It's maybe looking at the radius, how far away something is in terms of like an orbit. It's not super important. But, team, when you're right near the surface of the sun, bam, you're getting the whole intensity, okay? Or from a certain distance, you might have a certain amount of intensity, but what is it showing from here to here? From here to here, I am doubling the distance. If I'm doubling the distance and light is spreading out, the intensity is going down by not half, it's the distance squared. It's in fact 1/4. 2 squared is 4, and it's getting weaker. So I put that 4 in the denominator. If I'm triple the distance, well, 3 squared is 9, but the intensity, the strength is in the denominator because it's getting weaker. This graph is showing this thing called the inverse square law. This is the inverse square law right here. What it's getting at is how strong or how intense something is, whether it's sunlight or butter or paint from a spray paint can. The intensity, it's getting weaker with distance, and that's why distance is in the denominator, and it's getting weaker with the distance squared. Okay, and this is a graph representing this same effect. This is like the y-axis. Down here, this is like x. So it's similar to y is related to 1/x squared. All right. Again, as we're getting double and triple the distance, the intensity of the spray paint is getting weaker. It's getting weaker by 1 over the distance squared. All right. So here is just the basic definition in a sentence. The inverse square law is simply the pattern that the strength of something, whether that's butter thickness or pressure or paint from a spray paint can, it decreases with the square of the distance. If something is following the inverse square law, that means it's following this relationship. The force or the brightness or the loudness, it has distance squared in the denominator. And team, if that looked familiar, oh boy, good for you, because we have seen 2 physics equations that follow the inverse square law. We learned that the force of gravity, I'm going to start on the bottom. The force of gravity is based on the mass of objects, and it's based on how far away these objects are. The strength of gravity, how strong it is, gets weaker and weaker with distance, but it gets weaker with distance squared. Imagine the force of gravity is spreading out, or Einstein's version, that warping of space and time, that bending is getting weaker as it's getting stretched in the square in kind of 2 dimensions as it's spreading out. That's at least a decent way to think about it. And team, our Coulomb's law, our electric force, same thing. The force between charges, it's based on the charges themselves, and it's based on the distance. The strength gets weaker as distance increases, and it gets weaker by the inverse square law. Anything that follows this pattern, we say, follows that inverse square law. Can you think of other things? What else follows the inverse square law? What else decreases in intensity with the square of the distance? Or even if you're not sure if it's the square of the distance, how about just what do you think is getting weaker the farther it has to travel? When you're farther away from the source, what seems to get weaker and weaker? There's actually, everybody, a whole bunch of examples. We've already talked about these too, but it turns out like radiation, think of, I don't know, man, whether it's like a nuclear bomb or a nuclear reactor, that stuff is dangerous, but the strength of that radioactive decay gets weaker and weaker the farther away you are. That's why you're not worried right now about a nuclear power plant down in Southern California. You're so far away that potential danger is super teeny tiny. Sound, of course, everybody, you know that when you're farther away from a speaker, the sound's volume gets quieter, it gets weaker. The intensity of volume gets less and less. It turns out that volume, that sound, follows this inverse square law in light. Everybody, think of a candle or a source of light, a flashlight. Farther and farther away it is, the less bright it seems to be. There are other things that also follow this pattern, that when you're farther away, yeah, it spreads out, but it's also getting weaker, okay? Not everything exactly follows d squared, but there are many things in our world, in our universe, that follow this idea. And team, just to bring it home, I just want to focus again on the fact that this inverse square law is kind of showing two different things, and both are important. The first is that things spread out as they travel. Light from the sun, classic example, okay? When you are a certain distance away, the light has spread out a certain amount. If you were twice as far, notice I have distance here, and then I'm twice as far away, the light has spread out. It has spread out by the distance squared. 2 squared is 4. So here the light was just making it through one of these rectangles. Now it would make it through 2 squared, 4. If I'm thrice 3 times as far away, it's going to spread out and cover 3 squared. That's 9. So the amount of spreading is based on the distance squared, but also the intensity, the strength of that light or sound or gravity or whatever. It's the inverse of that square. So over here, the area is 2 squared is 4. The intensity is the inverse, 1 divided by 4. Here, the area is now 9 times. The intensity is 1/9. So the area is based on the square. It's spreading out basically like length and height, or width and height, if you will. And the intensity, because now it has to spread out amongst all those areas, is the inverse of that square. Oh man, that's weird. It's kind of a mouthful. That's the idea. Last thing, everybody, this is not really a physics thing, but we are in the age of TikTok and YouTube and people wanting to be influencers. If you are someone who is interested in the idea of like recording yourself for social media, photography is majorly based on this idea of the inverse square law. It is huge in photography and taking videos. Maybe you already know that lighting a subject is very important if you're trying to film, but that lighting, because it follows the inverse square law, depending on what your effects you want them to be, or just you want to be a clear image in front of the camera, you keeping in mind of the inverse square law, how light behaves, is actually a very big deal if you are trying to be someone who is really trying to professionally get their leg in or get experience with YouTube or TikTok or whatever social media or video-based service that you can think of, all right? Anyway, that's a non-physics example. The inverse square law is a big deal in photography or someone who is interested in uploading videos and things like that. But that's the inverse square law, all right? Thanks a lot for watching this video.